Hello everyone, welcome. So today is lecture 61. Although this course was supposed to end by lecture 60, but because of the nature of the content we have to spill over here in lecture 61. So what we are going to do today is we'll continue from where we were in the last lecture on fixture and packages, and we'll very briefly talk about power amplifier, the classes of operation of power amplifier, and that should be the end of this course and of course this module also. Okay. So over to the whiteboard here. So in the last lecture we are talking about the fixture. A fixture is essentially this interface that enables you to measure a discrete device or a die or a packaged device, because oftentimes it may not be feasible to measure them on wafer. So you can see these connectors. These connectors will be connected to the equipment, which is for instance a vector network analyzer, right? And this is your device, for instance. Okay, these are microstrip lines. Okay, these are printed on the board. The white thing you see, that is like your board. It's often an alumina substrate, a low loss alumina substrate. Below that there could be a board, a metallic board or whatever, and then it enables you to basically bring the RF signal, okay, and you can measure that and it can come out and you can again measure it here. Okay, because oftentimes, as you can see, and I showed you in the last lecture, it may not be possible to do on wafer measurement. Okay, the device may be very large periphery and your GSG probes may not be able to do that, because its periphery is much larger than the probe pitch of your ground signal probe tips. So you have a GSG configuration here, for instance, and that is feeding into this large like a bond pad from where you are wire bonding this device, and this device is fixed on this metal platform which is on this board. Okay, this is the entire fixture actually, and these are alumina substrate, the white ones, low loss, on which you are basically having this giant bond pad and the microstrip lines and the GSG pads. Okay, it enables you to measure this device not on wafer but in a fixture. Okay. Although on wafer measurements are extremely popular, accurate, common, and they are very easy in a way that you can also build models, but these are also very critical, this fixture based measurements. Okay. In many cases these bond wires that you see could be a part of the de-embedding. You might want to de-embed them, or you might want to include them in the model of the device that you are going to sell to a customer, for instance. Okay. But this is a bare die, a discrete die, you can say, discrete device, but in many cases actually in real application you need to package the device, because package is going to protect the device from things like moisture, dirt, or mechanical vibration. It will basically give the protection to the device, and so also it helps you dissipate the heat away, because power transistors, specifically power transistors, they dissipate a lot of heat. Even if it is not a power transistor, you would have a package for protecting the surface, the device from all these different issues that might come up. So this for instance is the fixture. Can you see that this is a fixture, and here you may not have a GSG. In here you had a GSG here, but here you do not have a GSG because you are not going to bring in the probe tips. In this case you actually, in this particular configuration, you are bringing the RF probe tips here. Okay, but in this configuration you are actually not going to bring in the RF probe tips, you are going to bring the connector, just like this image I showed, like that. So you have, see, this is the connection to the vector network analyzer VNA, that is called SMA connector. That connector is coming here, and this is the mechanical blocks that you are going to fix with this the mechanical block that is sandwiched in between. This is your fixture board. This fixture board is going to be bolted, like mechanically bolted to the metal structure below. You can see this screws here, I mean the holes here. You are going to bolt them down, and these white areas are again alumina that is going to be providing a low loss platform for these microstrip lines. Can you see these microstrip lines coming in? And so this connector you see, they are going to connect this SMA connector to this microstrip line that you see here. So there is a SMA connector like this to a microstrip line connection interface. So there is an interface where your RF signal is coming in a cable that is basically forced to travel on a planar semiconductor substrate. That is what is going to happen here, right. This is your active device that you have put on the fixture, and you might have wire bonds, for instance, okay, bonding that. And this mechanical assembly that you see, okay, this mechanical support and assembly can be used for many things. First of all, you can have a thermocouple here to measure the temperature of the back of the chuck, of this plane, this metallic plane that you see. This is a metallic plane, correct? This is a metal carrier, we call them. It also provides a ground plane. This entire metallic plane on which the fixture is, the fixture has this metallic plane. This metallic plane provides a common or a global ground plane. So you do not have multiple grounds, you have a common global ground. So there is no ground discontinuity, and this mechanical support that you see, you can, for instance, it can take the heat away. You can flow in liquid actually. you can have liquid channels. I will show you. You can have liquid channels, so that if it is a very high power transistor, air cooling or fan cooling may not be sufficient. So, you might have to flow liquid to cool them. So, this mechanical structure can enable you to flow liquid through it. So, it will take the heat away. You can have a thermocouple here inserted, so that will also measure in real time the temperature of the fixture, or eventually the back of the fixture or the device, you can say. So, there are many functions of this mechanical assembly, and the alumina substrate of course provides the low loss platform on the microstrip line. So, I hope you got the the concept of what is happening here, and the size of this of course can change. You can design this and fabricate it, manufactured with a local vendor. You can actually make these fixtures at your local shop, for instance. People there are vendors who actually make these locally, based on the device size, the fixture size, etc., etc. Okay. This is this particular thing, the zoomed image of this. You can see exactly this is the fixture, and for instance, you are going to define a reference plane here. That is your reference plane. Remember we talked about reference plane. So, you are going to measure till then. I mean, you are going to de-embed till then, for instance, all this microstrip line, all the connections, etc. You are going to de-embed till then. What it means is that this bond pad and the bond wires that will come eventually. There is no device here, by the way. It is an empty assembly. Okay. So, these bond wires and bond pads could be a part of the actual device that you are going to sell to the or give to the designer or the customer. So, they could be a part of the device. So, you are going to de-embed till this plane, for instance, everything till this plane you might have to de-embed. So, you can see in some cases after you put down the device, sometimes people put this is a plastic encapsulation, like it is like an over the mold, you can fill in with plastic everywhere. So, it will also have it protects the device, it gives its good protection against mechanical vibration, for instance, dirt, etc., etc. So, again depends on the particular application, depends on the power levels and things like that, but you can choose to have this encapsulation on top of that, okay, and then you have to de-embed till this point. For a few millimeter gate width, multi-finger devices, you have few millimeter that will dissipate few watts maybe of power, it is okay, but if you have very large power transistor, power RF transistor, then things might look little different. You might have to do a proper more careful packaging. So, people also have fixtures. I will come to package, by the way. People also use fixtures to measure package devices. So, you can see this is the package device here. Can you see that outline here? This is a package flange and this is the package device. The entire package can be actually measured on a fixture. So, in this case this is the fixture, with all this mechanical support you see, everything is a fixture. And what is this, like a line here? That is actually like an impedance transformation line. So, what it means is that when you package the device, and if it is a very high power transistor, your impedances at the input and output could be very, very low. When you say very, very low, it could be like say 1 ohm, 2 ohm. Then what happens is that it is almost at the edge of the Smith chart, and then impedance matching becomes very difficult. So, because everything else is 50 ohm in a way, you can say that. So, you want to kind of bring this 1 to 2 ohm to a level of 50 ohm. So, you have to do some pre-matching, okay, and you need to transform the impedance. You have to transform the impedance of the surrounding 50 ohm to something like say 5 or 10 ohm, so that matching to this 1 or 2 ohm becomes more convenient or easier, okay. And oftentimes what happens is that if you have packaged power transistors, measuring S parameter accurately could be difficult. So, you need to have this kind of a impedance transformation, okay. And you have to understand that if you have very high power transistor, your automatic load pull systems are not often available. You have to do a manual tuning based load pull. What is load pull? Load pull helps you, it is a setup, it is a system that helps you measure the output power of this kind of devices. So, then in manual tuner, it is a manual, you can say it is a manual load pull. You may not have a large impedance range to match to 1 or 2 ohm, so then that is why you need to do this impedance transformation, okay. You can see this clamp here, this clamp is going to pressurize this device there, so that it forms a very good connection to the flange and the carrier. This is the carrier, this is the carrier, it forms the carrier. You want to form a very good metallic connection there, so it puts a pressure so that there is no gap or vacuum there, okay. And this impedance transformation are implemented on the board, on the fixture, you can say, okay, and it could be all in the single PCB. So, maybe I will show you a picture here. So, this is an image, I will show you the book from which I took all of this mostly. This line you see here, this line, this is precisely this, this line, okay. So, that is an impedance transformation line, it is transforming the impedance, and in this case it is a Chebyshev transformer. So, impedance transformation can be of different configuration or types or techniques. This is Chebyshev transformer, and you are basically transforming from like 1 or 2 ohm to like a 5 ohm, so that you are helping match the transmission without being exactly at the edge of the Smith chart. Okay. So, for instance 10:1 transformation ratio, this transformer might do a 10:1 transformation ratio, which means a 1 ohm impedance could be transformed to a 5 ohm or vice versa, and that will help you match with the 50 ohm, okay, better. So, this part, this entire thing is actually a part of this. You can see that this is a part of the thing, this is the input, this is the output transformation, and this is the actual device which is packaged. You can see this is the connection to the instrument that you are going to measure. This is the connector. It's, as I told you, this connector is making this interface with the microstrip line that is bringing the wave in the planar substrate. You just have to understand that, and because it is a very high power transistor, it could be hundreds of watt, who knows. So, you are having to bring in liquid coolant here on the back side. This is the configuration. You can see the liquid comes in here, it flows like this, okay, and it takes the heat out. There is a motor, there is a pump, or there could be an self a circulant, a self-sustained circulation where you do not have to necessarily bring in fresh water all the time. It can just keep circulating the same water, and there is a fan to take the heat away from the water. Things like that can be arranged, but you need a liquid flow oftentimes at this fixture level, at this system level, where you are going to cool down the large power transistor. Okay. Although people are trying to do this kind of liquid cooling at the device level also, it is called embedded liquid cooling. So, what happens is that on the device level, this is package device, and package device is sitting on this entire fixture, which is sitting on a heat sink. Okay, this is a part of the heat sink, the copper which takes the heat away. Copper, actually it is a copper moly or a copper tungsten alloy, this heat sink that takes the heat away, and you do not have to flow in liquid all the time, but in many cases you do have to flow the liquid because the power may be really high, you dissipate enormous amount of heat. Okay, so people are trying to do this embedded cooling with, of course, not this giant these channels, but you have microfluidic channels, MF. So, the microfluidic channels could be embedded in the device. So, what I mean is that if you have a transistor, and these are high power transistor, so if you have like GaN, okay, and the GaN could be on say silicon or silicon carbide, you etch the silicon carbide and you bring in liquid in, liquid out. So, the liquid is coming very close to the actual 2D electron gas where the heat is generated. See, here the liquid is kind of far away, you have the package, you have the flange, and you have the metallic fixture, and you have below. So, it is quite far away, although it takes the heat away, but the heat taking away, the heat extraction will be much more efficient when your liquid is flowing very close to the active channel, but you cannot bring it too close because it will affect the impedances of the RF. So, there are many things there. This is an active area of research, just to mention here. Okay. Then these are different kinds of packages specifically used for power RF transistors, such as high voltage LDMOS or gallium nitride transistor that dissipate a lot of RF power. Sometimes if it is there is a two flanges, essentially there is a gate flange, there is a drain flange. Sometimes you might have two on each side if it is really high power, there are two drain, two gate, for instance. These are all metal, these are air cavity ceramic packages, which means there is a ceramic and there is a air cavity, and then you are basically putting this lid on top of that, and we will show a blown up image of that. And then this is like a plastic over molded. This is relatively low cost and volume production. This is little high cost, and this is for more high performance. Although plastic packages are also being actively improvised so that they are coming close to air cavity. There is a hybrid of both of them approach, plastic as well as air cavity, to get the benefit of low cost, high volume as well as superior performance of ceramic. So, this is for instance the metal ceramic cavity blown up image, and this is the overmolded plastic package. In general they are very similar with some differences. For instance, you have this flange which is a copper tungsten alloy I told you. On top of that you have this window frame. It's a blown up image of the package, by the way, where you are going to put the device. Okay, and this is one lid, maybe this could be the drain lid or this could be the gate lid, for instance, and these are made of something like nickel iron alloy. Then they are gold plated. The choice of this alloy is determined by kind of things like how much heat it can take away, how much conductivity is providing, skin depth, etc., many things are there. But this is a nickel iron alloy, and then there is a gold plate. Everything looks like golden because there is a gold plating. Okay, gold is a noble, it does not react so much with the atmosphere, so it is good. Okay, and then on top you have this ceramic lid, which is attached using a epoxy. It's like a polymer, you can say, and then you fill it up, and it's air basically. So, you basically put the device and you have this lid that you will encapsulate with. Over molded plastic is very similar, except that these are something called mold locks. You are going to help enhance the adhesion of the mold compound, because here you will fill up not with air but with a plastic. It's a molded plastic, so you will fill up with the molded plastic, and so you will help improve the adhesion of the mole compound, whatever you are using as a mole compound, and this is a lid for this could be for instance a copper or some kind of alloy. So, you are going to improve the adhesion. So, you need these mole locks to help increase that adhesion, and this is a plastic encapsulation of course. Okay, you have to understand that this is like filled with plastic, it can be over molded. So, it's plastic is flown or it's poured over top, you can say it's flown over that, and you want to increase the adhesion of the mole compound. Okay, so that's why you have this mole locks. Okay, there. Packaging is a different concept. I mean, it's if you want to study packaging, it's again a full semester course on its own, because there are so many things about taking the heat away and things like that. There is a QFN package which is very popular and common. It's also low cost. QFN stands for quad flat no lid. Unlike this packages where you have a lid coming out, here you have no lid. Can you see that? There is no lid here. You just have these pins. I mean, you can see this. There is no lid here. It's very popular for RF chips also. And these are typical small sizes, maybe a few millimeter or maybe less than that. Okay, and these are very lightweight because there are no lids and there is no wires. You can see it's very low inductance. Okay, and inside that you can see these images show you that this is taken from the internet, from Keysight. You can see that the internet image is shown here. So, there is a microstrip line feeding in, and then there are all these different pads are there, maybe the ground pad, the signal pad, and many kinds of pads are there, and you will have a wire bond to connect, for instance, one input and one output. From here, this is the output and this is the input, and you can see that this is the active chip and this is the board. You can have via holes, by the way, to connect it to the ground. If you have a ground plane below, you can create via holes to connect this ground, wherever the ground is, to the board below. Okay, so this is the bottom view of the QFN and this is the top view of the QFN. Okay, this is how the inside of the QFN package looks like. These pins are used essentially to bring in the signal, the microstrip signal. Okay, so with that I believe we are ending this discussion on package, and we will move to the basics of power amplifier very soon. But this is the book that I had referred to for most of these discussions on packaging and fixture and things like that. So, from now we will transition smoothly to some basic concepts of power amplifier, because the last few minutes we are talking mostly about high power transistor and how taking the heat away, for instance, is difficult, and you need to be able to handle so much high power in a power amplifier and transistors for power amplifier. So, we are going to talk about power amplifier. So, maybe I can create a whiteboard here. So, we will just touch very briefly upon a power amplifier. Okay, we have talked about transistors for power amplifier, specifically LDMOS, silicon LDMOS is a very dominant contender, and then gallium nitride, of course, which is very emerging. Gallium arsenide based FETs also have been used as power amplifier. They are still used as power amplifiers, by the way, but the real high power, like things like in wireless base station, cell phone base stations, which we also call cell phone towers, the kind of power levels that you need there is enormous, and so gallium arsenide is not used. It is typically gallium nitride and LDMOS. That is not to say that gallium arsenide is not used at all. It is used in many other things in base station, maybe the LNA, the low noise amplifier, maybe switches, mixers, etc. But the power amplifier is typically LDMOS and gallium nitride, especially for really high power amplifiers, tens of watts, hundreds of watts kind of thing. Okay. Now, power amplifier is a very vast topic, very complicated, very detailed. You probably need more than 2 full semester courses to understand power amplifier, and many years of practice as a designer to actually appreciate what power amplifiers are. But here, in the context of this course, it is neither the mandate nor the requisite to understand power amplifier, but we will just go through extremely basics of the power amplifier, which is basically the classes of operation of power amplifier. That is all we are going to talk about. Okay, it is in no way treatment of power amplifier, just the introduction, more than a pre-introduction actually. Okay, so before we talk about the classes of operation, you have to understand that today's and this is in the context of wireless communication mostly. Okay, although power amplifiers are also very important for strategic or military radars, satellite communication, very important, as we discussed in the initial part of this course, lecture 3 and 4 probably. But wireless communication is where there are the most stringent considerations come. When I say most stringent consideration, there are things like how much output power you are going to get, correct, from an amplifier, how much gain you are offering, how much of efficiency it has, and then there is things like linearity. Okay, there is things like footprint or the size, okay, the size, and of course the weight, the heat dissipation, okay, then cost, then things like time to market. Even if it is low cost, the time to market may be large. Okay, the thing is, all of this have very conflicting requirements. In other words, when you try to improve one of the parameters, many other parameters go for a toss, and these constraints are increasingly becoming more difficult to tolerate, or they are more stringent as we are talking today, and it puts an enormous pressure on the power amplifier designer to design better and better power amplifier, because it is the most power hungry block. It guzzles up the most amount of power in your RF chip, you can say, it is the most power hungry block, and so its efficiency is the most critical parameter, but you cannot sacrifice many other things. You have to, some of them, but that is how the life is, and so for instance, you have a mobile phone. All of us has a mobile phone. Mobile phone has a power amplifier, of course, and that power amplifier is often a gallium arsenide based HBT, heterojunction bipolar transistor, correct, because it will handle maybe 1 to 2 watts of power in your cell phone. You are going to charge, and then the battery, it will drain the battery lifetime depends on this power amplifier mostly. So your power amplifier in the cell phone, the constraints that you have are enormous, because it directly impacts the battery life, correct. This is the cell phone power amplifier, but then it's going to receive signal, and then it's also going to transmit signal to the nearest base station, correct. The base station is transmitting. So the base station, we are talking about much higher power levels, because it's going to transmit signals to the entire neighborhood maybe. So the base station powers are much more higher, maybe few hundred watts, okay. And so the base station power amplifier is mostly LDMOS or gallium nitride. It's not one LDMOS or one gallium nitride. You need to have a module, or you need to have what is called today nowadays the way you transmit, and this is power amplifier, by the way, is used in transmission, TX we call it. So transmission, when you transmit the signal, you have to boost the power, you have to amplify the power of the signal and then transmit to the nearest base station, for instance, or the base station will boost the power and transmit to all the receivers or all the cell phone holders in that vicinity or in that locality. So the power has to be really boosted up and then sent out, okay. And that's what the power amplifier does, right. That's how the power amplifier does, and it's typically LDMOS or gallium nitride that you use in a base station, a cell phone base station. We call it cellular infrastructure application, okay. And more and more improvisation are done in the transmission itself in terms of the antenna design. There are concepts that you might have heard about, things like massive MIMO. These are and then beam forming, okay. Beam forming and then phased array, okay. Although phased array radars have been popular for a long time, but in the cellular civilian application like a cell phone base station also, people are now adopting the phased array beam forming application, where essentially you are going to direct you do not want to isotropically emit the signal everywhere, because it is a waste. You direct it to the desired direction and you do it electronically, kind of, okay. You do not change the direction of the antenna direction remains constant, but by changing the phases of the signals, you have many antenna elements. And these antenna elements will emit these waveforms, the RF waveforms with a delay, so that there is every waveform will look like there is a constant waveform that is coming, but there is an increasing delay with a phase shift. You are introducing the delay among these different elements. These are different antenna elements, and each antenna element may be driven by an RF chip, could be an MMIC, okay. There might be a power amplifier, for instance, okay. There could be a power amplifier. So you have this beam forming that is done, and then you need power amplifiers for the same. So these are more advanced techniques that are employed in things like base station, although this have been used in military radars for a long time, this beam forming, this phase array concept, okay. But what I am trying to say is that there are more constraints on the device designer to trade off different parameters. All of these different parameters have to be traded off one for the other, and that is how power amplifier designs come up, okay. Now we have to understand it in wireless communication. The RF signal does not go in as a single sine wave. These are digitally modulated. Which means you are going to put some digital modulation scheme on top of this RF wave, okay. Things like quadrature amplitude modulation or orthogonal frequency division multiplexing. We are not going to talk about these schemes, but these are modulating schemes, multiplexing schemes, you can say, okay. So what happens to your signal will have different intensity and with different frequencies, okay. So if I am plotting the normalized power of the signal that you are transmitting, okay, and this is time with respect to time, it will look, the power levels might look something like that. Some powers will be high, some powers will be low. So your average power might be this, okay, but the peak power is very high. So this is called the peak to average power ratio, okay, the peak to average ratio, or PAPR, peak to average power ratio. And this is a very important parameter, because this peak to average ratio is now large, because you have this digital modulation schemes, and when you have this large peak to average ratio, which means your peak power could be very high compared to the average power that you are transmitting. You see, in a normal sine wave you just have a average and then you have a peak, it is very small, right, but here it can be crazy. So because you have a very large peak to average power ratio, and that is because you have this very complicated digital modulation schemes that you are using now. So what happens is that you have to operate a power amplifier at something called back off, okay, you have to operate at something called back off. Now what is back off? Okay, that is very important to understand before you understand any class of operation, which is, you know, class of operation is okay, but this back off concept is very important. So we need to first look at three important things. If I am going to plot the output power of a power amplifier, you can say power transistor in this case also, okay, and you are looking at the input power. First things to understand is that instead of milliwatt or watt, people refer to it as dBm, and I told you dBm is nothing but, you know, 10 log of the power that you are talking about divided by 1 milliwatt to the base 10. This is your dBm. So roughly I can say, not roughly, 10 dBm, okay, 20 dBm. This is just easy to remember and it's good actually, okay. 30 dBm is 1 watt, 20 dBm is 0.1 watt or 100 milliwatt, and 10 dBm is 10 milliwatt, and 1 dBm is 1 milliwatt, okay. Just remember that 40 dBm, it is a log scale, so it goes crazy, is 10 watt, and 50 dBm is very high, it is 100 watt, okay, it is crazy, 100 watt, okay, just remember that. So we are going to, it's good to remember that. It's so if you supply the input power, by the way, in RF signal, no, although we bias the transistor at a certain current and voltage, you know, for instance the drain voltage I have biased it at 28 volt for a base station application, and the current biasing, the question point on current is 0.5 times the maximum current you are getting. So maximum current, if it is say 2 amps, you are going to bias it at 1 amp, half of that. So you bias it at a certain current, you bias it at a certain voltage, but the power, but the RF signal that you bring in, no, you do not denote it with a power, a voltage or a current, you denote it with power. So you say I am bringing in a power, an input RF signal of certain power. So when I increase the power, input power, my output power also increase, and that is the gain, right. So my input power and output power will go linearly, that is the linear part of the transistor. Then it starts saturating and then it saturates, correct. This is the output power, and this is in it is in dBm, and this is also in dBm, and the ratio of both of them is your gain. So if I choose say a blue color, so the gain, if I plot gain with blue color, and the gain will be in dB, the ratio of two parameters in dBm will be dB. So you can subtract the output by input in dBm, or you can take the ratio, that is the same, okay. So the gain, so gain will stay flat, okay, and at this point the power is getting saturated, so we call this gain compression. So the gain will start compressing like that, and the gain will start compressing like that. So this is your gain is compressing, it's reducing, okay. This is your flat gain, okay, this is a flat gain. So this part is like your linear portion. When I say linear, it is not the transistor IV linear, it is the linearity of the amplifier, the power transistor. This is the linear part, beyond that the power is saturating, so the gain is falling off, alright, the gain is falling off. By the way, you are giving a constant DC power to the amplifier, you can say the transistor, and you are also bringing in an input RF power on top of that, and you are going to get output RF power, right. You are going to dissipate some heat also, by the way, it is not 100% efficient, you are going to dissipate some heat, right. So now what is happening is that this is a gain compression, the blue one, right. So if this was some gain, suppose this value is constant at say 15 dB, that is your gain, okay, which means output by output power minus input power is 15 dB, okay. Then you constant dB 15, you see at what point it has become 14 dB, it will decrease, no, 14, 13, 12, etc., it will decrease, right. So this point is your called 1 dB compression point. So that at that point the gain is compressed by 1 dB, so it is say 14 dB of gain here, and that 14 dB of gain corresponds to this power level here, for instance. So, you can define the power at 1 dB compression point. This is suppose your 3 dB compression point, which means this value is 12 dB. It is 3 dB lower than that here, right. So, 3 dB compression point. So, you can define the power here. So, this is your 3 dB compression point. Typically people use 1 dB and 3 dB compression point to define the output power of the transistor or the amplifier. Okay. So, that is your power that is defined. Now, the fundamental question is, why does it compress, the gain compress, why does the power saturate? This is the nonlinearity coming in. Essentially you are going to lose out power. So, see, you are talking about a fundamental frequency f naught, okay, but you are inherently going to have harmonics 2f naught, 3f naught, because it is a highly nonlinear system, it is a highly nonlinear device. So, you are going to lose out power specifically to the third harmonic, and because you are losing out power to the third harmonic, you are going to get, because you are going to higher and higher powers, the amount of power you are losing to the third harmonic also increases. So, you are going to get this compression, okay. And another way of looking at it is that you are going to increase, as you are going to increase the input power, you are going to increase the voltage and the current swings in a way, okay. The voltage swing, you know, if you recall the IDVD characteristics look like that, right. So, you are operating in this part only, but the moment the voltage is swinging here, the voltage is hitting the knee. So, you are trying to push the voltage more and more in the knee region to get larger voltage swing. So, as soon as you approach the knee region, you are going to get compression in the power, because you are approaching nonlinearity, the knee is highly nonlinear. So, you basically try to compress the gain, that is what is going to happen here. Now, in this particular plot I am also going to use the black color for something called power added efficiency. The power added efficiency is the single most critical parameter, you can say it is one of the most important parameter, and this power added efficiency, okay, is expressed as the drain efficiency into 1 minus 1 by gain. Now, what is drain efficiency? Drain efficiency is nothing but the output power you are getting in RF divided by the DC power that you are supplying, okay. Some DC power you are constantly supplying, irrespective of where you are on this, your DC power is constant. You are increasing the RF power input power in this direction, okay. So, as you are increasing the RF power input in this direction, your output power is also increasing, and that is why this drain efficiency is increasing. You see my point? The drain efficiency is output RF power divided by the DC bias that you are supplying, DC power. The DC power is constant. So, the output power is increasing as you are increasing the input power. You saw the red curve here, and so this ratio is your drain efficiency, and the drain efficiency is increasing, and the gain is constant, because this multiplied by 1 minus 1 by G is your power added efficiency, and gain is constant until that point. So, your power added efficiency, if I plot the black line, is going to increase, it is going to increase. However, at one point the gain becomes really low, the gain is compressing. So, this factor becomes very low, so the power added efficiency will drop like that. So, this is your peak power added efficiency, PAE. It is a very important parameter, because power added efficiency also accounts for the input RF power that you are giving by incorporating this gain G here, okay. So, the power added efficiency is that point. Now, I told you in the last slide that because of this complex digital modulation scheme, you have to operate in something called back off. Now, what is back off? This is precisely the thing. So, I am going to plot the plot again. So, this is your output power, this is your input power, okay. Your efficiency, or you can say the let me first plot the efficiency, the PAE. The PAE is going to get like that, right, and then I am going to change the color here, and I am going to plot the gain. The gain is constant and it decreases, right. So, this is your suppose 1 dB compression point. This is all, this part is basically the power is saturated, it is compression. You cannot operate the device at this point, because you know, if you look at this, the signal is, average power is here, but the peak signal is here, you are going to get significant distortion beyond this point. So, you have to operate in this part, the linear part where the gain is linear, that is called back off. Now, when you say 5 dB back off, I am operating at 5 dB back off, that means this point, suppose you define this point as some input power, suppose this is some x dBm, okay. I am going to come here, and this I am going to come here 5 dB. If this is x dBm, I am going to subtract 5 dB from there. So, suppose this is your 20 dBm, which means it is 10 milliwatt of power. I am going to come to 15 dBm. So, I am going to come to 15 dBm, 5 dB I have reduced from this point, this 1 dB compression point. So, I am calling this point as the 5 dB back off point, okay. So maybe and people define this from 1 dB compression point, people may define it from some other point, but essentially you are defining a reference and at the compression, and beyond that, or maybe you can define at this point, so you come from that point by 5 dB or 7 dB or whatever to this side. So you are talking about this part where it is highly linear, okay, because of linearity constraints you are having to do that. You are going to operate at lower power essentially. This, when you say back off, you are basically operating at a linear part, and that is a linearity consideration by the way, because the gain is linear here, and you are operating at a lower input power, which means you are operating at a lower output power. By the way, that also means if you look at the black curve here, if your efficiency, this is your PA, your PA is also reducing. So your efficiency is also kind of low to modest, but it is still better than say a very linear class, but you still have your linearity consideration is forcing you to operate at back off. That means you are not operating at the saturation, and because your efficiency curve goes like that, and this is your saturation, you cannot operate there because your voltage, your power swings are so much because of the digital modulation scheme. So you are forcing yourself to operate here. So your efficiency, this is your efficiency plot, correct, your efficiency is also low. So efficiency is also low in the back off, but you have no option, you need to operate at back off to ensure that you are at the linear part of the power profile here, okay. So these understandings are very important, and I will not go much more into now all these things, but I will just come to the classes of operation. But before that, I have to tell you about very quickly about the schematic. Essentially, if you have a power amplifier, okay, you need to have an output matching because the impedance has to be matched. We have talked about impedance matching so much, and then you are going to deliver the output power to some load here, correct, some load here, and then you are going to supply a DC, your DC power has, and DC voltage and current you are giving, no. So there is a DC of course that you are going to give, and then you are going to bring in the RF input. So you have a say an RF signal, this is the source resistance of the RF signal, and then you are going to bring it here, right, and then the power that you are giving in here is called P in, which is delivered, that is the power delivered here, and this is the P in that you are bringing from the source, but some power may be reflected back. You want to minimize that also, but sometimes you cannot help, so it is the power that is reflected back, okay, just keep that in mind, okay. So there is something called GT, it is called transducer gain, and there is something called GP, which is called power gain. So transducer gain is basically your output power that you get, the output power divided by the input power that you are bringing in from the source, that is your transducer gain, and the power gain is defined as the output power, which is this, divided by the delivered power, the power that is actually delivered. You do not account for the reflected power. So this quantity will be better in a way because the denominator is lower, okay, because some power is always reflected in a way. In ideal case these are same, but in general. So this is your definition, just a quick definition that I have to tell you. And if I am going to say that because you are going to get output power here, one thing that we did not talk about here is that you are bringing the input power at a certain frequency f0, which is called the fundamental frequency, right, and you are going to you want to deliver power at the same frequency f0, but you are going to get some harmonics, you are going to get at 2f0, 3f0 and so on. These are higher order harmonics of the fundamental frequency where you may or you will be getting some power, and that is not a desired thing because ideally you would not want to get power in those harmonics. So you have to terminate them appropriately, okay, and the more nonlinear a device is, the more power you are going to get there, but then with all these harmonics you can exploit them to advantage to improve the efficiency or the efficiency linearity trade off, okay. So essentially the output, the DC power that you are supplying and the input power that you are bringing in at the fundamental frequency, the two of them together is equal to the output power that you are getting at the fundamental frequency plus the output power that you are getting at all these higher order harmonics plus the power that is dissipated in the amplifier, because you are going to get some heat out, okay, that is inevitable. You cannot have 100% efficient power conversion, so you are going to get some heat out of that, okay. So with this background, I guess we can quickly go through the basics of the power amplifier classes now. So when I say class of operation, it is basically about biasing the device, that is all, okay. What biasing conditions are you use? So if I plot the IDVD characteristics of a transistor, if you recall that the IDVD characteristics look like that, right, it looks like that, okay, and then this beyond this point is the breakdown. So this is your VD max and this is your V knee, okay, the knee voltage, right. So, essentially you are going to, this is your ID max. So, your current can swing maximum between this and this 0 to ID max, and the voltage can swing maximum between this and this, the knee voltage to the drain voltage, I mean the maximum drain voltage, which is basically the breakdown voltage. Although you slightly keep it below the breakdown, the swing, the biasing point is this, is the VQ, the drain biasing point, which is half of this, half of the breakdown minus, although it is you do not exactly go to breakdown, V knee by 2, that is your drain swing, you can say the drain bias essentially, and the current bias is of course ID max by 2, right. So, when you bias it at this kind of a situation where the current can swing half exactly, okay, and this is a load line, this load line will come like, you define a load line, no, this is the load line along which you are operating the swing, the device. So, when the current is maximum here at swinging at this point, your voltage is the lowest here at the knee voltage. When the voltage is maximum here, the current is swinging to the minimum here 0. So, if the voltage waveform looks like that, right, then your current waveform will look like that, they are 180 degree out of phase, right, but there is overlap, there is significant overlap between the voltage and the current, and this device is always on, this device never turns off. Can you see that? This is never turning off, it is always on, it is always on, it is called class A, okay. It gives you very good power because you are operating on the entire plane of this DC IV plane, we call it the DC IV plane. Of course, the more you approach the knee, you are getting compression, but you are operating the entire DC IV plane. It is the most linear operation, it is the most linear, there is no clipping of the sine wave, it is the most linear operation, there is maximum overlap between the voltage and the current here. So, there you have the maximum, and because it is always on, the maximum theoretically achievable efficiency is 50%, not good for cellular infrastructures handset application, okay, because 50% efficiency will really drain the battery very fast. Although it gives you the best output power, it gives you the best linearity, but you have to you cannot choose it, but it is useful for things where efficiency does not matter, where linearity is the most important, maybe audio amplifier. So, this is very this is the very fundamental class of operation, it is called class A. Now, there are higher classes, say class AB, then class B, and then class C, and we will not talk about beyond that, they are more complicated, class F, J, F inverse, J inverse, etc. But these are 3 classes we will just quickly talk about. You are basically engineering the waveform, you are trying to reduce, as you come down from class AB to B to C, you are reducing the overlap between the voltage and the current waveforms. The more you reduce the overlap between voltage and current, the better your efficiency is, but the output power and the gain and the linearity, they all suffer, they all suffer. Your gain will be lower, your output power will be lower because you are not going to exploit the entire DC IV plane, and your linearity will be worse, but you are going to get benefit on efficiency. So, people choose to operate in this direction. You can have at the system level, you can introduce some blocks like a digital pre-distortion block to improve the linearity, for instance. It adds to the complexity, but there is no way out. With higher efficiency, you have to go to higher classes of operation. So, when I say higher class of operation, if you recall the IV characteristics here, I have this, and I told you the load line is this for class A. So, what happens in class AB is that your load line will be something like this. You are not operating on the entire you are not going to operate on the entire plane of the device, okay. You are not going to operate on the entire plane of the device, you are essentially clipping, you can actually come down like that. You are going to, you will have the allowed voltage swing, but your current will be clipped, which means if I am looking at ID versus VG, suppose I have this, okay, I am going to bias it close to pinch off. So, the current swing that is going to have here, this is pinch off, no, this part is clipped, there is no current there, and if I bias it, suppose this is the thing, okay, this is IDVG, if I bias it exactly at pinch off, that is your class C, oh sorry, that is class B, you are biasing exactly at pinch off, then essentially half of the cycle of the sine of the current, there is no current because it is below pinch off. So, it is clipped off, only for the half you have current. So, clipping off, you are reducing the overlap with the voltage waveform. Your voltage will swing entirely from knee to your breakdown, but your current will not exist for a substantial part of this voltage swing, it will only exist for half of this current swing. In class C, you can go even below pinch off, and what will happen is that if you bias even below pinch off, so if you have this, you are going to bias here, you are going to get current only here, this entire thing is off. So you are even reducing the, you are increasing the clipping of the waveform significantly, so that you are minimizing the overlap between the current and the voltage even more, and this helps you increase the efficiency. That is all basically is all about the classes of operation. So what I can say is that in class A your device is on for the entire period. So for if I say this is one cycle, you know, then this is a angle theta, this is 2 pi or 360 degree. So I can say the device is on for the entire 360 degree. So this I call as the conduction angle, it is conducting for entire 360 degree angle. So this conduction angle is a very important part of defining the class of operation. So for class A it is on for the entire cycle, so its conduction angle is 2 pi, it is always on. Okay. So if I plot the normalized current density versus for instance this conduction angle, okay, so maybe the device is on for certain time, but then it is off, this is 0 for okay off, okay, and then it is on. So this part is off. So if this is my conduction angle, say alpha by 2, then this and this is maybe my alpha. So you know I have it off for certain angle, I have on it on for certain angle, this is a higher class of operation. So you are basically, if your class A looks like that, okay, maybe I can use a blue color here, class AB will look like this, you are biasing closer to pinch off, okay, and maybe class B will look even steeper because you are biasing at pinch off, it is a sine wave, sorry, okay, my drawing is not very good, but it is clipped like that. And class C is biased even crazy, right. So maybe I can use a different color here, and class C will be something like this, you are reducing the overlap between the voltage and the current, you are increasing the efficiency, you are basically reducing the conduction angle. So for instance in class A I told you 360 degree is the conduction angle, in class B the conduction angle is 180 degree, that means it is on for exactly only half of the cycle, the half is off, which is a biased at pinch off. In class AB you are between 360 to 180 degree, between the maximum output current, half of the maximum output current to the pinch off condition. In class C it can be 90 degree for instance, you are even below the pinch off, okay. So when you have this below pinch off, at pinch off, then you are going to clip the waveform, no, so that increases the non-linearity of the device, of the system, and it introduces higher order components. So you will get harmonic, second harmonic, third harmonic, etc. Those harmonic components can be exploited to your advantage. It increases the efficiency, okay, your overall efficiency of the device will increase. So class A maximum 50%, class B is maximum 78.5% efficiency, AB is between 50 to 78%, and class C can be up to 90% efficient, although you are going to lose out heavily on linearity and power gain and output power. You are occupying lower and lower portion of the DC IV curve plane. So your output power also reduces, but your efficiency improves. So these conflicting trade-offs make it very hard for a power PA designer, you know, life is very hard that way, but there is no way out, this is the way to increase the efficiency, okay. So I think with that we will conclude today's lecture, because this is only the very basics of some of the things about power amplifier that we talked about how much efficiency matters, the classes of operation, the saturation, the compression, the back off, the high power peak to average ratio, but there are so many other things. Hopefully there will be more and there are, I guess, power amplifier design courses and that are needed for you to appreciate the power amplifier design. But with that we will conclude this lecture here today and also this module, and that is also brings us to the conclusion of this course. Hopefully you learned as much during this course going through this lecture as I learned while preparing for these lectures. So you know, we will be in touch, and of course there will be question and answer sessions that I will interact with you face to face. But thank you for being in this journey with me, and thanks for your time. Thank you.